And why don't we continue with your talk, Marius?
Yes, thank you. So, hi everybody. Let me first share my screen. 1 second. Okay, now you should see my screen, right? Okay. So today I'm going to talk about a recent paper that we published in which we investigate how the changes of inter-areal coherence between field potentials can be predicted by connectivity and oscillatory power. Oh, 1 second. Okay. So there have been many papers that pointed out that in a distributed network of a brain with different specialized brain areas, you need some mechanism to coordinate the activity across brain areas. And many different authors have proposed that phase synchronization could be such a mechanism, whereby different areas become synchronized, which allows them then to communicate more effectively. So the idea behind this hypothesis is that synchronization allows the brain to form transient ensembles of neurons in different areas that then become coupled, which allows them to boost their communication. So these kind of interactions can be studied on different scales by recording from different brain areas. So you can observe it either on a local scale, recording single units, but you can also observe these interactions on a mesoscale level using LFP signals, ECOG, EEG, or MEG signals. So what many studies in the past have done is to record LFP signals from multiple brain areas and then use measures like coherence or Granger causality to see how interactions of brain areas depend on a cognitive or behavioral condition. So as I mentioned, coherence and Granger causality are most frequently measured using local field potentials. And we know that electric field potentials are generated through transmembrane currents. And the main contributor of these currents are actually synaptic currents that themselves generate extracellular return currents. And another important point that I want to make here is that even though we call the local field potential a local field potential, it's not only reflecting local activity of a certain area, because any kind of synaptic input that comes into an area will generate an extracellular current that then also is a part of this local field potentials that we measure. So it can be driven by local as well as afferent synaptic inputs. So now let's dive into some data. This dataset has been recorded by Benjamin Dan in the lab of Hans-Jörg Scherberger in Göttingen, where they recorded from 2 areas of a macaque monkey during a memory-guided reach task. And when we look at the power spectrum of the LFP signal, you can see a quite strong beta oscillation in area 7B. And this comes along with a strong spike field locking of the units in area 7B, which we quantify here using PPC, which is an index that is proportional to the squared spike field coherence, but normalizes for firing rate. And at the same time, area F5 doesn't show any oscillatory activity or any phase locking of the single units. So this phase lock, so what's surprising then is that when we quantify the coherence between the different field potentials of the 2 areas, you can see a quite clear narrow peak at the frequency range at which this area 7B oscillates. And that raises the question now, how can you have this clear beta coherence peak between these 2 areas, which might suggest some sort of oscillatory coupling, but you have no local rhythm in area F5, neither any spike field locking from area 5 units to area F5 units to the local field in area 7B. So regarding this observation, we then came up with a model to predict how coherence emerges and changes depending on various factors. And the mechanism behind this model is very basic. And the essential idea is that inter-areal coherence can be explained by the fact that outputs from one area give rise to synaptic inputs in the same area through recurrent connections, as well as to correlate synaptic inputs in another brain area, which we refer to as synaptic source mixing. And of course, we're not the first to describe this mechanism. So there have been several papers that detail this mechanism more on a biophysical side. So we started out building a simplified LFP model where a sender signal is composed out of an oscillatory term as well as a 1/f noise term. And this sender signal is then linearly imposed on a receiver area, which just contains a 1/f background fluctuation. And subsequently, you see a coherence as well as Granger causality peak emerge at the oscillatory frequency of the sender signal. And as a next step, we then derived an analytic solution to predict coherence based on the connectivity parameter W here and a parameter alpha, which we call sender oscillation strength, which is the ratio of the oscillation in the sender and the receiver area. So you can see that inter-areal coherence in this model increases with coupling weight as well as with an increase in the sender oscillation strength. So now there is another factor that we identified, which is what we call source projection coherence. So in this model that I just showed you, we assume that this projected signal is fully coherent with the signal in the source area that projects. But this assumption is not very realistic, as the neurons that project to another area are only a small subset of a population of neurons in this projecting area. So not all neurons of this projecting area not all neurons will project from one area to the next, and that means that the activity of this projecting subset will not be entirely coherent with the local population. And again, for this, we can also derive an analytic equation for this source projection coherence. And without going too much into details here, you can see that this coherence between the projecting subset of neurons and the total sender population depends on the number of projecting neurons. So this is quite intuitive. The more neurons that project, the more this projecting subset will be coherent with the sender signal. And it also depends on the spike field phase locking, which here is denoted as PPC. So the higher the local spike field locking, the higher the coherence between this projecting subset and the sender population will be. So that now leads to a final equation where the inter-areal coherence between two brain areas depends on the connection weight, the sender oscillation strength, as well as the source projection coherence. So next, now we tested our model by looking into different behavioral periods of this macaque memory grasping task that I just showed you. So during this task, the power spectrum of area 7B shows a significant decrease in beta power, while the power spectrum of area F5 remains almost unchanged. And this comes along with a strong decrease in beta coherence between the two field potentials of the different areas. And as you can see in the bottom plot, when we now fit our model to the power spectrum and the coherence spectrum, we don't require a strong change in the connection weight. So the connection weight between those two different areas is not significantly different, even though the coherence shows a very strong decrease, which suggests that we can explain this change in coherence purely by the change in oscillations in the sender area, and there's no need for a change in effective communication or synaptic gain, which is here modeled as this connection weight parameter. So now we wanted to test whether this model generalizes onto other data sets. So we looked into the LN visual coding data set, where they recorded from different visual areas in the mouse using neuropixel probes. And after we first identified the different layers of V1, we evaluated the coherence between LGN and V1. And as you can see here, we see a quite strong coherence peak at layer 4 at the 60 Hertz frequency range. And as you can see here in this bottom plot, the neurons in LGN show a quite strong phase locking to this local rhythm in LGN, to the local population, while most neurons in V1 don't show this phase locking. And as you can see here, only a small fractions of neurons in layer 4 of V1 show phase locking to this strong rhythm in LGN. So now we are wondering whether this coherence peak that we see between the field potentials is mostly driven by the afferent synaptic inputs, or whether you need the spiking entrainment in V1. And furthermore, we wanted to test whether we can explain behavioral state changes in LGN V1 coherence using our model. So next, we separated periods of high and low arousal based on pupil diameter. And as you can see here, during the periods of high arousal, this local gamma phase locking in LGN increases quite strongly. And this comes along with an increase in inter-areal coherence. So consistent with the predictions from our model, we found that the increase in LGN-V1 gamma coherence is proportional to the increase in local LGN gamma phase locking. So now we wanted to finally test our hypothesis in a causal experiment. So my great colleagues Anna and Sissi recorded from a somatostatin Cree mouse line using neuropixel probes. And while stimulating V1 with a laser, we silenced most of the pyramidal and PV cells by stimulating these somatostatin cells. And as you can see in this plot, the power spectrum of area V1 barely changes. So this strong gamma peak in area V1 doesn't disappear when we silence V1 firing. And furthermore, we also observed that this gamma coherence peak still remains despite this strong silencing of V1 neurons. So this result confirms our hypothesis that inter-areal coherence can be observed independently of spiking entrainment or oscillatory coupling across brain areas and doesn't need necessary entrainment of the neurons in this receiver area. So now in this last section, we wanted to investigate this problem in a more biological, realistic model. So in this case, each area is modeled as a network of excitatory and inhibitory neurons that are governed by Wilson-Cowan equations. So the coupling of inhibitory and excitatory neurons in each area is a possible mechanism that gives rise to local oscillations in a circuit. So now we construct two types of scenarios. In the scenario on the left, we propagate EPSPs from the sender area to the receiver area, but we make the neurons artificially blind to this input, so they don't get entrained by this rhythm of the sender area. While in the other case, the neurons in the receiver area get entrained by this rhythm of the sender area, and yeah, exactly, that's what we do. And now what you see here, that this entrainment only marginally increases the inter-areal coherence. So when you measure the local field potentials or the whole population, you cannot differentiate between the two cases, whether a receiver area listens to the rhythm of a sender area or not. So let's come to our conclusions. What we see is that coherence can arise by default from anatomical connections, and it does not require any form of oscillatory coupling or spiking entrainment. And it neither indicates any selective communication at a certain frequency. And in our model, coherence is a consequence of communication rather than a cause of it. And furthermore, our equation could be used to infer effective synaptic connectivity, even though this comes along with several difficulties that we discuss in our paper. So last but not least, I want to thank our great collaborators from Göttingen, Benjamin Swati and Hans-Jörg Scherberger, my supervisor, Martin Wink, as well as the whole Wink Lab for great support. Thank you.
Wonderful. I'll be clapping for everyone here. A great talk, truly exciting topic. Much of my PhD thesis was about interneuron synchronization. So I find that really exciting. So I want to start with Scott Rich's question. Is there a reason that you focused on SST interneurons optogenetically? Is it just a matter of the time course of the inhibition as opposed to the faster somatic inhibition from PV cells, for instance?
So one thing is that somatostatin neurons inhibit PV as well as pyramidal cells. That was one reason for that. But of course, we could also use PV neurons. And in fact, we actually did that. We didn't have the results when we published the paper, but we will have another publication at some point where we as well show that this works the same way with PV neurons. So there are some preliminary results, but yeah, both cases.
Wonderful. There I have a question by Sarah, who asked, isn't it that interneurons are the main contributors to gamma? Interesting that you have silenced PV cells and you still have gamma.
Exactly. So what we actually see when we differentiate the different neuron classes is that it's mostly the PV neurons that get entrained by this gamma rhythm. So that's why exactly we wanted to silence those PV neurons to see if it's necessary, this entrainment of the PV neurons to see this gamma rhythm in V1. But what we find is that actually these synaptic inputs are already enough to establish this local field in V1 layer 4. So of course the entrainment of the interneurons increases this coherence, but they are not necessary to establish it.
Cool. So, and here I have a question that is my own, which is we often use correlations to interpret about the flow of information in some area. But if the direct signal, basically the signal flowing there produces much of the signal, then this should mostly be just like a dirty version of actual structural connectivity. So I'm curious if your experiments and computational analysis lead you to think differently about how we should interpret correlation between brain regions in a way.
Yeah, that's a very important point. So I think one thing that we can conclude from this is that it's always useful to record single units, because only then you can really be sure how different areas, like how the neurons of different areas interact. So by recording the local field, we might say something about connectivity and structural changes, for example, but we cannot be sure how this really influences this correlation, the single neuron interactions. So I think one way around that is, of course, to really record from single units and to do manipulations, so you can see how things change while you, for example, silence a certain area or something like that. So I think you're completely right with that. Just the correlational evidence on this population level is not enough to say something about the real interactions between the different areas.
Cool, wonderful. Thanks again for the great